All right, hello class. Today we are starting chapter 18, and this is a change. If you've followed my other lectures, we've been talking about equilibrium for the last three chapters, and starting with this chapter, we're going to focus on energy and chemical reactions. Uh, and so it's a big change and we will see a tie between equilibrium and energy when we talk about Gibbs free energy later on. But I would say the main thing about this chapter is that you go back and look at chapter 5 in the Birch book and refresh your memory about delta H and enthalpy, heat of reaction. Those are all kind of the same topic. And then talk about endothermic, exothermic reactions. So go back and refresh your memory of chapter 5 in the Birch book. That'll make this chapter easier. If you don't do that, you're going to find that you struggle with this chapter, because what we're going to be talking about in this chapter is spontaneous processes. So spontaneous processes are like, we know the water falls over the falls, or we know the ball spontaneously rolls down the hill. We don't see the water go up the falls, and we don't see the ball roll up the hill on its own spontaneously. So there are two components that help us determine whether a reaction is spontaneous or not, and that is heat, delta H, enthalpy, that we've talked about, and chapter 5 in Chem 170, Gen Chem 1. And then we're going to bring in the other component, which is entropy. So entropy, it's a fancy word for disorder. So the higher the entropy, the more disorder. So that's what we're going to be looking at in this chapter. So spontaneous processes, these are processes, again, like the ball rolling up the hill or down the hill. Or how about this? Once you start burning some wood, it keeps burning, right? You can throw another log on the fire, it keeps burning. Once that process begins, it's a spontaneous process. So think about, that's a good one to think about. Think about burning. Let's say you're starting a campfire. Think about what it takes to start a campfire. Generally you have to have dry wood. You know that generally you have to start with small pieces of wood or paper or something to ignite the kindling. So those small pieces of wood or sticks, they have lots of surface area. They can interact with the air surrounding um, those small pieces of kindling. And so the oxygen can get to the outer pieces of the wood. You start off with a match or something, and you get the kindling going, and you got a fire, and then you lay a smaller log on there, and it starts burning, and eventually the fire takes off, as we say, and you can add more logs as the fire continues to burn. You know that wet wood doesn't burn as well as dry wood, because why is that? Why does wet wood not burn as well as dry wood? So just think about that. See if you can think of what the reason is. Well, wet wood means that you're going to have to convert that liquid water into gaseous water before you can even get to the temperature required to burn the wood, right? So that's the kind of things that we're going to be looking at in this chapter. The other thing you know is that once you burn the wood, what do you have left? Well, you have ashes. And those ashes occupy more space or more volume than the condensed piece of wood did. So that's what entropy is entropy can be thought of as disorder, and so the ash is much more disorderly than the solid piece of wood. You can also think of it as the ash occupies more space. So there's been a trend to talk about entropy in terms of space occupation. If there's more space available for a substance to occupy, then we're going to have a greater entropy there. So you're going to see that kind of discussed in this chapter as well. It's a statistical method of explaining entropy. So A process that does occur under specific sets of conditions is called a spontaneous process. It does occur, all right, and it does have to have specific conditions. We know that wood's not going to burn if you just put a match on a log, right? It generally doesn't set the log on fire. So there's a specific set of conditions that have to be met. And then if it does not occur under these specific conditions, it's called a non-spontaneous reaction. So speak the language, spontaneous and non-spontaneous. So here's some examples of spontaneous and reactions and non-spontaneous reactions. So you know at room temperature, ice does melt. That's a spontaneous process. You take a piece of ice, put it on the counter, as long as it's above freezing or 25 degrees Celsius room temperature, it is going to melt. But you don't see water freeze to a solid ice at room temperature. So it's a non-spontaneous process. If I add a piece of sodium metal to water, it reacts violently. You can look at the video of this on YouTube, but we don't see sodium hydroxide reacting with hydrogen and producing sodium metal in water. So what's important about this statement is we've been talking about equilibrium processes where things go in the forward direction, then go in the reverse, and we say those reactions are reversible and equilibrium can be established. But just like strong acids or strong bases, once the acid ionizes, the ions don't stick back together and form the strong acid, right? We don't. That's why we said chloride ion is a very weak conjugate base, because the chloride ion is not going to accept a hydrogen ion from water and form hydrochloric acid in the hydroxide ion. That does not happen. So that's what this is saying too. Once I put the sodium metal into water, it reacts, and it forms sodium hydroxide and hydrogen, but the reverse reaction doesn't happen. Same thing about the ball. Ball rolls spontaneously down the hill, but we don't see the ball roll spontaneously up the hill. Same thing with rust. You can see your car rust. You don't see the rust just magically repair itself and become the metal that it was originally. It doesn't happen. So that's what we're looking at. And then the last one is just to show you that under the right conditions, some reactions become spontaneous. So water does become ice at negative 10 degrees Celsius. That's spontaneous. But it doesn't melt at negative 10 degrees Celsius unless there's something else is applied to it. All right, so going back to chapter 5, this is what you should know already. And if you don't, I just can't stress enough to go back to chapter 5. And now it seems like it's, a whole new chapter to read. Hopefully you had this chapter not too long ago, like last semester, and you can go, oh yeah, I remember this. So the first one is methane, which is a major component of natural gas, react with oxygen. We call this combustion, and it forms carbon dioxide, gas, and water. Liquid, and you notice the change in enthalpy, which is the delta H. This is the standard enthalpy change. Standard enthalpy change, the not symbol here means standard, all right? And then this is change in enthalpy. That's the language we speak. If you want to call it the heat of reaction, some people call it that as well, but it's a negative value here. So negative means exothermic. That means heat is given off to the surroundings, and that's what we learned in chapter 5. So this is an exothermic reaction. It gives off quite a bit of heat, and that's why we use it to heat our homes. We also have hydrogen ions reacting with hydroxide ions to form water, and that's a spontaneous reaction. Again, exothermic reaction. And you go, why are these spontaneous? Why are these spontaneous? Well, under their conditions, and this is maybe I should try to write this a little better here if I can. Let me try this. Oops, that's not going to work for me. Let's see if this works better. So and this is just part of it. This isn't the whole thing, but both of these reactions, the reactants are here in energy, and this is the reaction progress here, and the products are here. And so after we get to what we call the activation energy, which we'll talk about, and that becomes, so activation energy is from where the reactant energy is to the top of this peak. That's in chapter 5 as well. But because the products are lower in energy than the reactants, when I say P minus R as far as energy goes, I'm going to get a negative value. Now this one's less negative than this one, so this reaction more likely to be spontaneous than this one. But then it says not all exothermic reactions are spontaneous. So here they have H2O liquid going to H2O solid, which we would call ice, and that it has a change in the standard enthalpy change of negative 6.01 kilojoules. So it is negative, it is exothermic. That means that, again, the water, this is not a chemical reaction, this is just a process. So here's H2O liquid, and then to go to H2O solid would be here. So there's not much of a change here, and that reaction is not spontaneous above 0 degrees Celsius. You guys know that ice doesn't, liquid water doesn't freeze above 0 degrees Celsius. So just because it's exothermic generally indicates, it says conditions are favorable for it to be spontaneous, but it's not always the case. So that means there must be another component besides thermicity, either exothermic or endothermic, to determine whether the reaction is spontaneous or not. And that's going to lead us to our next concept, which is entropy. So right here, so while exothermicity favors spontaneity, it cannot be the sole factor that determines spontaneity. So our next topic is entropy. And so entropy is, again, disorder. So here's how now the way they talk about it in this book, they're going to use a statistical way of describing it. So let's talk about this slide because I think it's important as a foundational piece to this. It says entropy, capital S, of a system is measured by how spread out or dispersed the system's energy is. So that's what I mean by space or positions that each particle can occupy. The more spread out the energy, the more spread out the mass, the more possibilities. All right, so it says the simplest interpretation of this is how spread out the system energy is in space. In other words, for a given system, the greater the volume it occupies, the greater its entropy. So we like this. This is a good way to describe it because what we can do here is we can say, okay, we understand why a solid doesn't have much entropy. It has a definite shape and a definite volume. The liquid, on the other hand, it takes whatever the shape of the container is. It does have freedom to move around. It does have a definite volume, though. It can only spread out so much. And then gas, each one of these gas molecules acts independently. It takes up definitely more space, spreads out that energy, and so gases are going to have the greatest entropy. So that's what we're getting at here. So there is a mathematical equation to explain this distribution of energy, and that is entropy is equal to the Boltzmann constant. I'm not asking you to memorize it, but there it is. But I do want you to look at those units there. Just look at the units. That's really important. So it's joules per Kelvin. So it is a temperature-dependent constant. And W is the number of energetically equivalent different ways the molecules in a system can be arranged. All right? How many ways can particles be arranged in a system? And it seems complex, but we can show it on the next slide here of what that looks like. All right, so here we have W equals X raised to the nth power. All right, so X is space, and how many places can that space occupy? So you can tell this side has more entropy than this side. And the reason why is there's more space, more volume for each one of these particles to occupy versus this one over here. So this reaction is going to be spontaneous, right? If this is a gas and I lift this divider up, the gas is spontaneously going to move to this side to spread out the energy so it can occupy more space. Now, we never see all of this go this way, right? We never see it spontaneously, all these particles move to one side after we remove the barrier. It'd be like all of a sudden, if this is oxygen, all of a sudden there's no oxygen on this side and you can't breathe over here on this side. That would be a problem. And the reason why that doesn't happen is there's more positions for these particles to occupy, and to force them all over to one side, you're decreasing entropy, you're decreasing positions, and you're decreasing the distribution of the energy. So this next slide, I hope really makes this clear. So let's look at it. So you got two particles, all right? You got two particles. So in the first arrangement, you have two particles, and here are the possible arrangements. It's two particles and two spaces, and here's my four possible arrangements. Both particles are in this quadrant. They're in opposite quadrants, but on this side. They're opposite quadrants on this side, and they're both on this one. All right, so they flipped here. The only difference between these two and these two is they flipped, and here they're, instead of the upper quadrant, they're lower. So we got two spaces. We're just focused on this. It can only be here or here. And we got two particles, and there's only two spaces to occupy. All right, so then let's make this clear here. These two spaces are this, all right, oops. And the two particles are this, okay? So here we have two particles again, so that's this part. But now when we take the barrier away, we have four quadrants. That's just to oversimplify it. We know there's more spaces in here these particles can occupy, but for just to simplify it, here's my possible choices. With four quadrants and two particles, these are all possible choices. So we have 16 possible arrangements. So more entropy, less entropy, more energy distribution, less energy distribution. And that's what we're talking about here. So again, we have entropy equals Boltzmann constant ln of W. And then again, let me just say this again here. W is equal to number of positions raised to the nth power, the number of particles. All right, so there's three different states possible for this system. One molecule on each side, both molecules on the left, and both molecules on the right. All right, so the most probable state is the one with the highest number of possible arrangements. In this case, the most probable state is when one molecule is on each side of the container. All right, so what they're saying there is this is much more probable because they're on each side of the container versus these two particles being on the same side of the container. Oops, I should go back and show that, I guess. So again, this is more probable where the molecules are on different sides of the container versus them being both in one quadrant of the container. Okay, so how do we calculate delta S? The change in entropy of the system, the standard entropy, and the qualitatively predicting the sign of standard changes in entropy. That's what we're going to focus on now. So change, we know that change is always final minus initial. So that's what we're looking at here. So the change in entropy of the system. Now remember what the system is. Again, this is from chapter 5. So if you don't know the difference between system, surroundings, and universe, you've got to go back and read chapter 5. So the system's what we're interested in studying, and the change is always final minus initial. So we substitute in the Boltzmann equation, and then they're solved for, remember, a negative on a logarithmic function means divided by, so that's why this looks like this. And then they substitute in for the distribution, x raised to the nth power, we get this. And then remember, when you take the log of something raised to a power, that brings this out, and we can put it in front of the ln. And so this is what we have. So you may be using that equation to solve for entropy changes. All right. So that's just a derivation, just for you to follow how we got from change in entropy to an actual algebraic equation to solve for entropy changes. All right, so then they simplify this even more or arrange it so that we can relate it to the change in entropy, and ultimately we get, for our final product, to show the relationship between entropy and volume is that the change in entropy is N number of moles times R, the gas constant, times the final volume divided by the initial volume. So we can do that. Remember, let me just kind of make a note of this. So what is Na? Na is Avogadro's number. That is the symbol they use to mean 6.022 times 10 to the 23rd. Some books do this, some don't, so I think it's worth talking about. So N, the number, the total number, is equal to N, the number of particles, times Avogadro's number. So that's what they're showing here, is how this simplifies to that. So it just says, determine the change in entropy of 1 mole of ideal gas originally confined to 1/2 of a 5-liter container when the gas is allowed to expand to fill the entire container at constant temperature. All right, so there's going to be some changes here, and these are things that you, hopefully through working the problems, you will be able to use these fluently. But instead of using the gas constant 0.008206 liter atmospheres mole Kelvin, because we're talking about energy, this is the R we're going to be using in chapters 18 and 19. So R is 8.314 joules per Kelvin mole, and the reason why we're using this value for R is because it has joules in it, and we're going to start relating entropy and thermicity to energy in joules. All right, N, lowercase n, is the number of moles, okay? And volume, the final volume is 5 liters. We were at 2.5, and then it expanded to 5, and the initial volume was 2.5, all right? So that's how we go, confined to 1/2 of the 5 liters. So initially we're at 2.5 liters, and we finally end up at 5 liters. So you don't have to know the derivation. You could just go back and memorize this equation here at the bottom. You could do that. But that's what we're going to use, right? We're going to use that equation to solve. And it's easy, right? I don't think this is that difficult. It's a plug and chug problem, which is you take the information that's given in the problem and then label it. Make sure you label it. And then you plug in the information. So R is here. Joules per Kelvin mole, N is the number of moles, and then the ln of the final volume minus the initial volume, and we get 5.8 times joules per Kelvin. All right, joules per Kelvin. So here's something I want you to make a note of. This is the units for entropy. Yes, there's a temperature dependency, and notice this is in joules, not kilojoules, and that's going to be a problem later on when we're delta H's are generally in enthalpy changes are generally kilojoules per mole. Entropy is joules per Kelvin, and we're going to have to work with those units to make sure that they're the same before we add them together. All right, so here's what's cool about entropy versus enthalpy. So remember with enthalpy, we had to artificially come up with what is a delta H of standard enthalpy change equal to 0. And we said that any element in its standard state at 25 degrees Celsius or 25 degrees Celsius is, or 0 degrees Celsius is, has an entropy of 0. So hydrogen, we said the standard, so its natural form, we said standard enthalpy of formation equals 0 for that, because that's its natural state as a gas. And so that's what we had to have a reference point, just like we say sea level is the reference point for height. But entropy is different. Entropy actually has an absolute value. It says it is possible to determine the absolute value of entropy of a substance. There is a 0 point, and that is the standard entropy of absolute entropy of a substance at 1 atmosphere at 0 Kelvin in a crystalline solid has an entropy of 0. All right? 0 Kelvin, no movement, crystalline solid, so it's very structured. It's not random. Will have a standard entropy of 0. So that means everything that you can think of beyond a perfect crystalline solid at 0 Kelvin is going to have a positive entropy value. And that's what you see in this chart here. So diamond's much more organized than graphite, and so graphite has a higher disorder, higher entropy than diamond does. So the more crystalline it is, oops, what did I do there? I'm looking at the wrong one. Yeah, this is water. Okay, well, water, this is liquid, this is gas. Liquids have less entropy than gas because they don't occupy as much space. So I was focused on this one. So diamond is 2.4. Look how low its entropy is compared to graphite, which is more than double that. So what's the difference again? Diamond looks like this. It's a network of carbons linked together. And it's a crystalline, it's a network. We call it a network solid. And so that's connected to another carbon like that. Graphite, though, looks like this. It's these hexagonal graphite. Each one of these corners has a carbon on it. And they form planes like so. And there'll be another plane below it just like this one. And this is what breaks off when you're writing with a graphite pencil. This breaks off and deposits on paper, and then this is left behind. So as you write more and more, this is peeling off these layers, and that's why your pencil gets dull. So what this is showing, though, I mean, easily I like this. It shows that liquids have less entropy than gases. Here's an important one right here. This is the one that gives students the most problem. These are both noble gases, but because neon has more electrons, it's going to have a greater entropy at the same temperature than helium, which only has 2 electrons. So if all things else are equal, everything else is equal, generally the larger the element, the more complex it is, the more entropy it has. And that's what this is talking about. So here's the one I want to stress, though, on this. This is the most missed part of determining entropy. Right here. For 2 monoatomic species, the one with the larger molar mass has the greatest entropy. Make sure you know that one. That's the most missed. So again, that's why neon has a greater entropy than helium. All right, and then the next one, same thing. One of the most missed is that one right there. So for 2 substances in the same phase with similar molar masses, so similar molar masses, same phase, the substance with the more complex molecular structure has the greatest standard entropy. So make sure you know that one. Again, That one and the other one are the most missed. Now to show that, let's look at the next slide. Alright, I'm having a little bit of problem here. Let's see what's going on. My slideshow has decided to quit on me. Let's see if this will do it. No, it's locked up. Alright, we'll stop here and I'll pick up here on the next video.